Da skal vi være på luften. Hjertelig velkommen. I can wish you heartily welcome, Dr. Alexander Karpov, live from Russia. I will give you the floor in a minute. I'll just turn to a brief introduction for tonight's lecture. Hjertelig velkommen til alle som følger med på denne livesendingen fra Teknisk museum. Det vil si rundt på våre distribuerte Teknisk museum. Vi fortsatt i hjemmekontor, men jeg kan også benytte anledningen nå til å bringe den gledelige nyheten av at museet som sådan faktisk kommer til å åpne denne uken. På fredag så åpner museene, og Teknisk museum er selvfølgelig blant dem som åpner. Så nå kan vi endelig etter 4 måneders stenging, ønske mer enn det til og med, snart et halvt års stenging, få lov til å ønske velkommen tilbake til Teknisk museum på Kjelsås. Dette er den 5. i rekken av videooverført foredrag i vår teknologihistoriske foredragsserie, og vi begynner jo å bli ganske drevne på dette også, og i dag skal vi virkelig utnytte fordelen av å bruke videoformatet og lære oss til dette her. Det er jo at vi kan knytte oss til en foredragsholder som kanskje ikke normalt ville vært i Oslo. Det vi skal på i dag er jo en reise inn i atomenes verden, og utgangspunktet er periodesystemet, og vi kjenner jo kanskje de fleste av oss periodesystemet, den tabellen som er oppslått i læreboka for 10. klasse bak meg her sånn. Det er den tabellen som gir orden til grunnstoffene etter stigende atomnummer. Men visste alle der ute at tabellen faktisk har et russisk opphav? Det var kjemikeren Dmitrij Ivanovitsj Mendelejev som satte opp de første 69 grunnstoffene etter dette periodeprinsippet for 152 år siden ble det vel. Så litt jubileum på litt etterskudd der er et utgangspunkt for dette arrangementet. Og siden denne gangen så har jo tabellen blitt utvidet med stadig flere grunnstoff, og dagens 118 blir jo også fortsatt utfordret av kjemikere og fysikere i hele verden som jobber på atomnivå, blant annet med å utvide den periodiske tabellen. Og en av dem som vi skal få møte her nå i dag da, er altså da dr. Alexander V. Karpov, som er vitenskapssekretær ved Flerov-laboratoriet i byen Dubna, som ligger et par timer nord for Moskva. Jeg kan kanskje kalle det for Russlands kjeller. Også fordi at det på Kjell er jo et kjent atomforskningsmiljø. Ikke riktig så stort som Flerov-laboratoriet riktig nok. For Flerov-laboratoriet, som da er oppkalt etter den russiske fysikeren Georgij N som ledet instituttet fra starten i 1957 og helt frem til 1989 faktisk. Altså Flerov-laboratoriet er et av flere institutter i det som kalles for fellesinstituttene for atomforskning, som ble opprettet som et internasjonalt forskningsinstitutt i Sovjetunionen i 1956, som et slags østblokkens CERN, som vi sa litt sånn høytidelig. Og etter 1990 så er jo det internasjonale preget utvidet enda mer gjennom samarbeid med både UNESCO og nettopp CERN, og i dag så har Fellesinstituttet over 5000 ansatte, og av dem så er 1200 høyt kvalifiserte forskere, og 1000 av dem er internasjonale forskere med doktorgrader innenfor atomforskning. Så dette er virkelig et stort internasjonalt laboratorium. Flerov-laboratoriet er Flerov-laboratoriet for kjernereaksjoner, som det heter. Det ble startet i 1957 som et av de første instituttene som var dedikert til kjernereaksjoner og utvikling av nye stabile elementer. Og jakten på nye grunnstoffer, det skjedde blant annet ved hjelp av verdens mest avanserte på den tiden, syklotron, som kom i drift i sin første utgave i 1970. Så hvis man lurer på hvordan det kan ha seg at periodesystemet vokser, så skyldes det altså at systematisk arbeid i blant annet av Flerov-laboratoriet. Grunnstoff 114 som har stabilisert seg og fått en plass i periodesystemet nå, det har til og med fått navnet Flerovium. Og dagens foredragsholder, som vi nå skal straks gi ordet til, Alexander V. Karpov, han er en av de som jobber videre med å finne stadig nye stoffer i kategorien superheavies, altså supertunge radioaktive stoffer. Og dette er jo selvfølgelig ikke noe masseprodukt som det kommer mange av daglig. Det siste hittil stabiliserte grunnstoffet nummer 118 det ble kunngjort i 2015 etter mange års forskning. Men det jobber altså videre med å få flere av disse stoffene i store internasjonale samarbeidsprosjekter, og selvfølgelig også en viss konkurranse. Og hvordan dette arbeidet foregår, og hva hensikten er med å sette sammen stoffer på denne måten og finne nye, det er det vi på en måte har invitert en av de fremste utøverne i dette faget til å fortelle oss om, og vi er veldig glad for det, at vi skal få høre det rett fra forskningsmiljøet selv, direkte på videolink da fra Dubna i Russland. Og Alexander Karpov, I'm happy to leave the floor to you after this brief introduction, where I've just told a bit about the background for the Flerov-laboratoriet and the hunt for the new super heavies. So please, Dr. Karpov, the floor is yours.
Thank you, Doug. Thank you very much for first invitation, yes, to give this talk, and second to your kind introduction. I didn't understand all, but some words, of course, I'm familiar with. Before starting my talk, I would like to pay attention to this epigraph, which was actually the words of founder of our laboratory, Georgij Flerov, explaining a scientific problem to high-rank officials. And I believe that taxpayers are among these high-rank officials. Try doing this not in the way it is correct, but in the way it is understandable. So it will be a noble lie. So with this, I would like to start my talk, which will be devoted to the periodic table of chemical elements. And in my talk, I would like to little bit touch, not even discuss, but touch some natural aspects of formation, of synthesis of these elements, and what we can do in the laboratories. Before starting this with the subject, I would like to say a few words about Institute. I understood that Doug already introduced the place where I'm working, but still I want to say a few words. So we are working in Joint Institute for Nuclear Research, which is international intergovernmental scientific organization. So it was founded in 1956. So this year we celebrate 65th anniversary of our institute. From the beginning, it was international, like CERN, which was founded 2 years before our institute. Agreement was signed in Moscow, and those time by 12 countries. Some of them do not exist anymore, but still institute exists. And from the beginning, the idea was and the purpose was in joining efforts for fundamental studies of the properties of matter. So today, as I said, we are 65. Institute has 18 member states. 6 countries are associated members. So among full members, for example, such European countries like Poland, Czech Republic, Slovak Republic. Among associated members, Germany and Italy and Hungary and Serbia. Of course, former Soviet Union republics are among full member states. Institute comprised of 7 laboratories, and each one with its own field of research, and the size of each laboratory is like a size of institute. We have a fleet of big scale, large scale, and indeed unique facilities. about 5,000 employers, 1,200 of them are scientists. Of course, very wide collaboration, so very often a number has changed, but roughly it's about 700 institutions in 63 countries. And the motto of the institute is "Science bringing nations together." I think that is really true. So let me start. Main content of my talk, which, as I said, is about periodic table of chemical elements. One of the most successful form of this periodic table was made by Dmitrij Mendelejev in 1869. He also formulates, not maybe exactly, but from the understanding of his time, it was correct. He formulated the periodic law of chemical elements, and this I think is even more important than periodic table itself, because table is table, but periodic law is a natural law, and of course, for the scientist, the law is more important than its representation in tables or whatever. This event, I mean, this discovery of Mendelejev was so important for society that 2019, year of 150th anniversary of the periodic table, was proclaimed by UNESCO and United Nations as an international year of the periodic table. I should mention then, in the time of Mendelejev, there was only 63 elements known, and it was enough finally to find this law and to place the elements in the proper way in this table. This initiative about proclaiming of the year 2019 as an international year of periodic table was indeed international initiative, and letters of support come from to UNESCO from many sides, many institutions, and our 5 cents to this initiative was a letter which was signed during the event, which was called International Colloquium, dedicated to the naming of super heavy elements with numbers 115, 117, 118. By the way, 118 is the heaviest element known today. And this letter was signed by directors of 3 institutes co-discoverers of this element. That was Joint Institute for Nuclear Research, Lawrence Livermore National Laboratory, and Oak Ridge National Laboratory, 2 last laboratories, that is national laboratories of United States. And you see that the last sentence says that we are participants of the colloquium, taking into account importance of the Mendelejev discoveries, support EU-PAC appeal to UNESCO on declaration of the year 2019 as the International Year of Periodic Table of Elements. I don't think that this very letter was decisive, but I hope that it was important to make this real. Well, let us now go back to the year 1896, and I think that all this story with our understanding of natural mechanisms of transformation of various elements, of synthesis of origination of various elements, was started from the discovery of radioactivity, which was made, as you know, by Antoine Henri Becquerel with his experiments with uranium salts. He got the Nobel Prize for this very important, indeed, discovery. There was then many brilliant observations, brilliant discoveries connected with names of such as Ernest Rutherford, Paul Villard, Marie and Pierre Curie, and many, many others. Several Nobel Prizes were given to these discoveries. In particular, Marie Curie got a Nobel Prize in Chemistry for discovery of radium and polonium, two radioactive elements. Different kind of radioactivities were found and finally explained. And the last point in all the story in discovery of basic types of radioactivity was made in 1940 by two young people. In those times, they were PhD students of Igor Kurchatov. There was Georgij Flerov and Konstantin Petržak. They made experiment and proof that nucleus can undergo fission in two parts, which was called spontaneous fission. Experiment was made actually in an underground laboratory, not in real laboratory. This was a subway station in Moscow, the deepest one in those times. That was 60 meters under the ground. All these discoveries connected with radioactivity allowed to find 7 new elements, radioactive elements, such as polonium, astatine, radon, francium, radium, actinium, and protactinium. Thorium and uranium were known already for many, many years before. So in this, with this discovery of radioactivity, we can find all 92 elements existing in the nature. And the last point was made, last element was discovered in 1940. So in 1940, we knew all elements which surround us. And of course, natural question is it all? Is the periodic table? Does periodic table is complete? Answer, of course, is no. And the question is why? Why we cannot find elements heavier than uranium? Answer is quite simple. The answer is the following: that on the Earth, our Earth is quite old planet. It is 4.5 billion years old, and on the Earth we can find only elements which either stable or live times comparable with the age of the Earth, so for billions of years. And uranium is the last element. It is radioactive, you know, but it lives billions of years, precisely 4.5 billions of years, 4.5 billions of years, and that is why we have uranium. Elements which heavier than element 92 uranium, they did exist in past. If I gave this talk some billions of years ago, so I think periodic table would be much larger. But they live shorter. I mean, elements heavier than uranium lives quite short, maybe millions of years, some of them millions of years, some of them thousands of years, some of them only seconds, and they simply decayed. So they didn't survive because of age of our planet. But these elements in principle may exist, and our in natural environment they can be produced. So somewhere in universe we can find places where we have elements heavy and maybe much heavier than uranium. And natural, again, wish of scientists is to try to complete the periodic table. If we cannot find something on the Earth and in the world which surround us, we can try to remake these elements artificially. And first case, when it was done, I mean, when it was shown that man can transform one element to another. It was made in 1919 by Ernest Rutherford. He showed that in order to transform one element to another, it is necessary to change its nucleus. And he collided helium nucleus with nitrogen nucleus and observe hydrogen nucleus, which is proton, and oxygen. It was not 100 years ago, but nearly 100 years ago, mankind became alchemists. So we knew how to transform one element to another. So not so long time ago, just 102 years ago, it became possible. What we can do? Of course, in laboratories, we can only adopt natural ways of producing elements, try to adopt for our conditions. For example, we can take uranium and put this uranium to some neutron source. This neutron source, for example, can be a nuclear reactor. This uranium, heaviest nucleus existing on the Earth, uranium-238. It lives for more than 4 billion years. It will capture neutron and became uranium-239. After 23 minutes only, it will decay, that is radioactive decay, it will decay to element 93, neptunium. Then neptunium may capture another neutron or decay to plutonium. And then neutron capture and decays, neutron capture and decays, and we will go step to the right, step up, step to the right, step up, and in this way we can produce after element 92, 93, 94, 95, 96, curium 97, 98, and so on, and go up to element 100 fermium. For that we should use special reactors, and not every reactors can be used for such purposes, but it is possible. It is possible in nuclear reactors to produce elements which are heavier than uranium, but with a certain limit. The limit is element 100, which is now called fermium, after Enrico Fermi. And element 100 is the heaviest element which can be produced in this way by radiation of uranium with neutrons. So this story was ended up in somewhere in 1960. Elements from 93 to 100 were discovered. This was all was this done in the United States, and nothing heavier than fermium was discovered in those time. So of course the next question, well, we can produce artificial elements, how we call them, transuranium elements, and we fill the periodic table up to element 100. The question is how many they are, how many elements can exist in nature in principle. In order to answer to this question, let us turn the subject a little bit and go and look to the universe and try to understand how elements were produced in the universe. What is the origination of chemical elements? This picture is more or less clear up to element 26, which is iron. So we more or less precisely know everything about origination of element up to element 26. But the question about origination of elements from fermium to uranium, at least 20 years ago, it was among the greatest unanswered question of physics, and this was one of the tasks formulated for 21st century. And the task the question looks as follows: how were the heavy elements from iron to uranium made? Time goes, yes, and at the moment, in my opinion, the question is not like how these elements were made, but where. And 2017 was a very important year to answer this question, because it was the year when gravitational waves were observed, and exactly this was gravitational waves produced by merge of two neutron stars. It is important discovery related to the general relativity of Einstein, but it's also important because it can potentially help, and it is already shown that it helps in understanding of nucleosynthesis process in the universe. And this very observation was the start of so-called multi-message astronomy. And I believe that in future this gives us the answer and understanding about astrophysical nucleosynthesis, about origination of all elements which we have on the Earth and even heavier. With lighter elements, this modern, on the modern level of understanding, we think that the first two elements like hydrogen and helium were produced just after Big Bang, in the beginning of formation of our universe. And elements themselves, or element, I mean nucleus and electrons surrounding this nucleus, were formed approximately 500 million years after the Big Bang. Before stars and galaxies were formed, our universe consists on 75% of hydrogen and on 25% of helium. So periodic table in the beginning of the universe look like this: only two elements and nothing else. It is interesting that even 9 million of years after, our universe is still almost completely made of hydrogen and helium. And all other elements make less than 1% of total amount of matter. That is a little bit contradictory to our everyday observation, because we see many things which are made of, I don't know, iron, copper, carbon, gold, and so on. But believe me that if we count amount of matter in the universe, not on our planet, but in the universe, so it will be almost 100% of hydrogen and helium. Elements which are heavier than helium can be produced in stars on different steps of evolution of stars. Everything starts from so-called burning of hydrogen, when finally 4 atoms of hydrogen produce 1 atom of helium. It is very, very unfavorable process and very long. And actually, we are very lucky that it is so long. So on our sun, it already goes for 4.5 billion, or maybe almost 5 billion years, and the same time left. If our sun would be 10 times bigger, so we didn't exist already at all, because our sun was already burned out. Then next step, 3 atoms of helium form 1 atom of element number 6, which is carbon. Then we can, if the star, our sun stops on the second step of producing of carbon. It is a very small star, and it cannot go beyond element number 6. But if stars are very massive, with the mass 15 times of mass of the sun, in principle, the process of synthesis, process of fusion can go to heavier and heavier elements, but not heavier than iron. That is the limit. That is the limit for synthesis, for thermonuclear synthesis in the star, element number 26. So after star burning, of massive star burning, most massive stars, periodic table should look like this. All elements from hydrogen up to iron. That's all in principle. So all elements which are heavier than iron should be produced somehow, and say, as I mentioned, 20 years ago, it was not really understood and clear how those elements can be produced and where it can be produced in the universe. And the ideas nowadays are that mainly 2 ideas. One, that in the end of evolution of massive stars, when iron is formed, so the star will be compress and compress and compress, and finally it will make a boom, which is called supernova explosion. And during this explosion, during this collapse of the core of the star and the explosion, iron and other quite heavy elements will be destroyed, will be completely destroyed to neutrons, protons, helium, and so on, electrons. So it will be like a soup of light particles, light nuclei and light particles. And all this soup during the explosion will irradiate nuclear material. And during this irradiation, and what it is important that among this soup we have a lot of neutrons, and these neutrons will be captured by nuclei, like it happened in nuclear reactors, but much amplified, billions of times amplified. And during this process, we can, from light elements, we can produce heavier and heavier and heavier. Actually, the question, how heavy can be elements produced in supernova explosions? Some estimations say that actually not very heavy. not very heavy. So the heaviest elements like, I don't know, gold, lead, or uranium cannot be produced even in this catastrophic event in the universe. The last hope is for another even more rare and more catastrophic event time to time happening in the universe, which is called a neutron star merger. Neutron stars are quite small objects, like only 10-20 kilometers in diameter, with huge mass, about mass of the sun. Sometimes they form so-called binary system, and one star rotates around another star, and after a certain time they can come closer and closer and finally merge, forming a black hole. And during this merging, gravitational waves are produced, and they were detected, as I mentioned, in 2017. But in the same time, a lot of material, and this material is rich of neutrons because it is a neutron star, is ejected from this point of collision, point of merger. And this material is indeed very heavy, and that is the place where heavy elements are produced. And already first observation of neutron star merger, which was mentioned 4 years ago, already showed that heavy elements like gold was produced during this single observed event. Now this modern technique allowing to detect gravitational waves as a signal of something interesting happening in the universe. We can, I think, in the future find much more information and finally answer on the question how elements are produced in the universe. And now let us go to our planet, to scientific laboratories, and discuss what we can do in laboratories to repeat, maybe to small extent, but repeat the nature, try to produce elements and their isotopes for fundamental science or for applications. I showed this slide before, that in 1960s, when already 100 elements were known, there was a question how many elements can be in principle. And to understand this, we should look to the slide, which is represents a kind of periodic table for nuclear physicists. It's called nuclear map, or map of nuclides, or nuclear chart. There are a lot of ways to name this. But this picture shows all nuclei which are composed of neutrons and protons, and so number of neutrons is the horizontal axis and number of protons in vertical axis. And colors show stability of nucleus. So each box, each cell is a nucleus made of certain number of neutrons and protons, and color gives you the stability. So black color is a stable nuclei, and the closer the color to blue, the shorter is half-life of element. If we look to upper part of this map, we can see the last really stable, absolutely stable nucleus, which is element which is lead 208, which is here, element 92, and two last elements which are very, very long-lived. That is thorium and uranium, element 90 and element 92. And you see that this mainland end up with lead, last stable element. Then we have a peninsula made of thorium and uranium. And as we go to elements heavier than uranium, to element 93, 94, and so on, you see that the colors change and goes closer and closer to the blue color. That means that stability is gradually lost. And if we come to element 100, we can observe elements which live maybe days and hours as maximum, not longer. So in 60 years ago, in 60s of 20th century, it was believed that if we continue producing new elements heavier than uranium, so we still can do this, but we cannot go much to elements much heavier than element 100. Maybe 104, maybe 105, maybe 106. And this will be the end of the periodic table because of stability, because elements live shorter and shorter, and finally simply this object which we can produce will be not an element anymore. So end of periodic table is very close. But in 1966, in two institutes, almost simultaneously, first in Dubna and second in Frankfurt University in Germany, it was predicted that everything is right, but if we go to elements which are much heavier than uranium, and these elements were called super heavy elements, so we can find a region around element 114 with neutron number 184, and this region will be a region of quite long-lived elements, not absolutely stable, but this element, this nuclei can live extremely long, maybe thousands of years, maybe billions. Some predictions said is that even billions of years could be half-lives of those elements. This region was named Island of Stability of super heavy elements, and since this prediction in 1966, there were many maybe tens of attempts to prove or disprove this prediction about existence of island of stability, to synthesize super heavy elements which should be members of this island in many laboratories worldwide. For example, here is the list of many main players and main laboratories which try to make this discovery of super heavy elements. As I said, all this story started in 1970, and during 15 years, all these laboratories except Tokyo, except Japan, like Los Alamos and Berkeley in the United States, Dubna Joint Institute for Nuclear Research, Oak Ridge National Laboratory, Mainz and Darmstadt in Germany, Orsay near the Paris in France, Würlingen in Switzerland, and some others try to produce super heavy elements. But yes, and ways to not only to produce, there are attempts to find them in nature, on the Earth or in some lunar object or in cosmic rays, to produce them artificially in laboratory, in nuclear reactors, even in nuclear explosions, not nuclear but thermonuclear explosions. I should mention that that was that element 99 and 100 were first discovered after the thermonuclear explosion, which was made in 1952. So the dust and some materials left after the explosion was collected and later on analyzed in Berkeley laboratory in the United States, and from that chemically two new elements, in those time new elements 99, which is now Einsteinium, and 100, and element 100, which is fermium, were discovered. Accelerators, of course, were used for synthesis of new elements. Many new apparatus were designed and manufactured, like accelerators, separators, detectors, different chemical methods, and so on. But unfortunately, in all attempts to produce super heavy elements, we didn't have any success. Didn't meet any success. In 80s, it was understood that the artificial synthesis of super heavy elements, acronym is SHE, is related to the reaction of synthesis. So the proper choice of the reaction which we should use for the synthesis is already half of the story. Studying nuclear reactions, excluding not perspective combinations which can be used in reactions. In the beginning of 90s, we in Dubna came to conclusion that the last hope and the only way to produce super heavy elements is to use a reaction of fusion of calcium-48, very rare isotope of calcium, and actinides, which are heavier than uranium. That is the only reaction which, in principle, can lead to discovery of super heavy elements. How it is made, let me first show how my daughter explained the problem of synthesis of super heavy or any element in the laboratory in school. So if you have an apple and watermelon and you collide apple and watermelon, so if you are lucky, you can produce a pumpkin. That is the way which is we nuclear physicists use in laboratories to synthesize new elements. Simply we substitute an apple with a calcium and watermelon, for example, with plutonium-244. We make a beam, we call it a beam, with the use of accelerator beam of calcium-48, and irradiated plutonium, which we call a target. Calcium is element number 20, plutonium is element 94. So if we collide calcium and plutonium and they will fuse, so they should form element 114, 20 protons in calcium, 94 protons in plutonium, 20 plus 94 gives 114, very simple arithmetics. So in this way we can produce this element, new nucleus, then it should pass through separator and we can detect it. Of course, plutonium is artificial material. As I said, that is uranium is last naturally abundant element. So plutonium element 94 we should produce artificially. As already I mentioned, we can do this with reactors. But to produce most heavy isotope of plutonium, plutonium-244, which we need for experiment, we use should use not simple reactor, but specialized reactors. And in the world, there are only two such reactors, one in the United States in Oak Ridge and another one in Russia in the city of Dmitrovgrad. And only these two reactors can produce material which we need for the target for such experiment. Amount of produced material is not really big. For this usually tens of milligrams as maximum. And the heaviest material which can be produced in such quantities, that is element 98 californium. So element 98 is the heaviest element which can be accumulated and produced in the quantities which we need for experiment. Calcium 48 is, we have the calcium 48, this isotope in all natural calcium, 0.2% of calcium, which we have a lot of calcium. It is calcium 48, but it is very difficult to separate calcium 48 from natural calcium. Nowadays, only in one place in the world it can be done. It is in Russia, in Ural mountain region, and annual production is only 10 grams of calcium 48. For example, in this picture, you see about 2 grams of calcium carbonate. And I think this amount would be enough for most expensive car. If you find the way how to sell it. A big problem was the careful use of calcium. And only in the end of 90s, technically, we were ready to use calcium 48 for thousands of hours annually. Thousands of hours we needed to make these experiments. And only this development of technique of ion sources, the picture of one of them is shown here, quite complicated device. Only in the end of 90s this became possible. Accelerator. This was accelerator U400 in Dubna, and it was optimized and upgraded again in 90s, optimized for this experiments with calcium 48. In those time, it was the most productive accelerator in this field of research. So it produced ions of calcium with intensity almost 10 to the 13 ions per second, huge intensity. And this velocity which we need, that is approximately 10% speed of light. That is the condition of experiment. Experiment itself looks like this. So after we make an accelerator, we put very important part, ion source on the top. So we are ready to start acceleration of calcium. Ions of calcium produced in ion source come to the chamber of the cyclotron. They are accelerated, making spiral trajectories. Then they go to the beam channel, finally to the target, made, for example, of berkelium nuclei, and berkelium is an element 97. It allowed to produce element 113, which pass through separator and finally come to the detector. And in this detector, we can observe radioactive decay of element 113. First alpha decay give element 115, then second alpha decay element 113, then element 111, 109, 107, And finally, roughly in 1 minute, element 113 decays to dubnium element 105. Dubnium lives for more than 1 day, and then it fissions into fragments. That is how looks one event of synthesis of super heavy elements. How often we can observe this? Not really so often. After all these efforts which we made in 90s for preparation of the experiment, we can synthesize roughly 1 atom a week if we are lucky. For example, in the case of heaviest element 118, there was 1 atom a month. So that is not really, how to say, weight quantities. That is really single atoms. However, first experiment was made in started in 1999 with synthesis of element 114, and of course there was very important success, very important observation only of 3 events of synthesis of element 114. Then almost immediately experiments started for synthesis of elements 116, and then heavier and heavier and heavier elements. But what was important also, not only that we finally can synthesize super heavy elements, but also that we see that as we go to this cross, which should be the top of the island of stability, half-lives of the elements increase. So the elements start to live, nuclei start to live longer and longer and longer. On average, each neutron which we add to the nucleus increase lifetime approximately 10 times. This was extremely important observation, and that was a proof that island of stability, which was predicted in 60s, really exists. We till now didn't succeed to explore the top of island of stability. Nuclei which we synthesized are shown here, so we somehow touch the shore of this island, but we already see that it really exists. We don't know exactly. We do not exactly know where is the top. We have some ideas where it should be, but we know that the island of stability exists. All the story, there was a story of approximately 17 years from the first experiment up to final proof of discovery and final naming of the elements. And I should say that 5 heaviest elements, which we know nowadays, were discovered in Dubna, and in particular, this is element 114, named after Georgij Flerov, and element 119, named after Yuri Aganesian, leader of this research in the world, really, not only in our institute. And I also should say that that is the second time in history when element is named after a living person. The first case was element 106, Seborgium, named after Glenn Seaborg. Some elements like livermorium and tennessine are named, these names were suggested by our American colleagues because experiments which were made in Dubna were made in very broad collaboration. First of all, collaboration of 3 institutions, so that is Dubna, Livermore National Laboratory, and Oak Ridge National Laboratory, which is located in state Tennessee. And of course, you see names of these institutes, names of these places in the periodic table. Moscovium, of course, named after the region where Dubna is located. Coming to the end, I should say that since 1955, 18 elements from 101 up to 118 were synthesized. And for 10 of them, we have full or partial priority. I mean Dubna. So approximately 10% of the periodic table was discovered in the Joint Institute for Nuclear Research. Our future, of course, connected linked to the new equipment. Equipment which was best in the field 20 years ago, now is anymore not modern at all. We cannot go forward with this old equipment. So after 20 years, we had to rebuild everything. And we built a new facility, which is called the Factory of Super Heavy Elements. And in Dubna, it will be the center for future super heavy element research. New accelerator, which 10 times more powerful in terms of intensity than the previous accelerator. Its name of this machine is DC 280. DC means Dubna cyclotron. So it's work of our engineers. A new separator, which is almost 3 times more efficient in collecting super heavy atoms and guiding them to the detector. And our main plans for the future, that is, of course, a detailed study of already known super heavy elements. We discovered them, as I showed, we named them, we know some basic things about these elements, but still a lot of information remaining about these elements unknown. That is, first of all, and or in particular, that is chemical properties of new elements. First experiments already were made, but still these experiments are not enough, not sufficient to answer on the question of chemical properties of these extremely heavy elements. And of course, we understand that periodic table is not complete anymore. Still not complete. So attempts to synthesize elements heavier than element Y19 should be made, and our plans is to make these attempts for element 119 and 120. Just to finish my talk, I would like to show a movie which was specially prepared for the closing ceremony of the International Year of the Periodic Table. And this short movie show all the history of discovery, synthesis of elements in Dubna. Started from the element 102, element 104, Liverfordium, that is Georgij Flerov. You see on the picture again, Georgij Flerov. Element 103. They put in chronological way, so not in the order of element numbers, but in chronological way. Dubnium, element 105. Here on the picture you see Flerov and Jan Oganessian. 1979, very important year because of making new equipment. Element 107 was discovered then. Then a course of calcium-48 started with element 114. I mentioned this. Different ships going to the island of stability from the thorium and uranium plutonium peninsula. Yuri Oganessian showing the way. We are going element 115 with thorium. There was old separator which was used for all the story. That is how we fill gaps in the chart of nucleides, that official decision on names of super heavy elements like flerovium, livermorium, and other heaviest elements. That is our new equipment, our new facility, super heavy element factory, and our plans for future with studying of known elements and synthesis of element 119 and 120. So thank you very much. Thank you very much for your attention, and I hope that it was understandable.
Yes, thank you very much, Dr. Karpov. It was certainly understandable, and I really enjoyed the historical view that you gave, and also the practical insights and the fine images from your new facilities. And congratulations on them. And I always think it's interesting to reflect on how the development of the instruments themselves and the research facilities also broaden the knowledge that we can have on the world. We had a fantastic interested group of followers through this whole lecture. There have been some questions along the way. I could just pass on one of the questions that I had myself, of course, being not into the basic science myself. We always tend to think, well, what's the use of it? And of course, we all know that apart from the obvious, as the question is phrased here, apart from the obvious technical developments and breakthroughs to allow for the success of these experiments, what is the practical outcome of discovering super heavy elements?
Yeah, actually, I have back slides just about that, but I can say it without slides. Of course, elements themselves, the super heavy elements, have at the moment, and I think even in distant future, have no application. The answer is very simple, because we produce only single atoms of them. So in order to apply elements, we should produce in some measurable quantities like nanograms, milligrams, or I don't know, kilograms or tons. That is the case of transuranium elements like plutonium, americium, or californium, used for various equipment for, I don't know, in oil industry like californium, for example, or various medical applications, but not the story of super heavy elements. But still, you are right, technologies are very important. For example, accelerators and our knowledge which we gain about nuclear reactions is used in medicine. For example, all this nuclear medicine, all this radiopharmaceuticals, yes, this would be impossible without fundamental research, without all this cyclotrons, nuclear reactions, and so on. And of course, that is already our life. Tumor treatment with proton beams, or with carbon beams, or even some ideas of this maybe heavier beams for tumor therapy. That is also one important application. In our laboratory, we also do some research for this radio isotopes for various applications, but also we, for example, produce such materials which is called track membranes. This idea came from fundamental science, and it is a way how to produce from polymer film, very thin film, irradiated by using accelerators by heavy ions, then treated chemically to produce very nicely shaped pores in polymer, and in this way you can produce membranes. with numerous of applications. First of all, again, in medicine and in industry. For example, in semiconductor industry, where you need extremely pure water. So final stage of purification is called water polishing. Is made with track membranes, made with the use of accelerators. Cancer diagnostics, I don't know, many things which, and this field is really growing. Worldwide, all the space program would be impossible without testing of electronics on radiation resistance, because in space and even in nearest space and also in all these distant missions, we have a cosmic rays, and they're very dangerous for electronics. So we should test this electronics before sending, I don't know, satellites or some space ships to the space. All this PET tomography, many things I can mention, and many things originate from this research.
Yes, thank you.
Of course, in the beginning, we simply don't know. We simply don't know how it can be applied or cannot be applied at all. But all our history says that we never think about application, making fundamental research. We always have only one idea: to understand the nature, understand the laws of nature. And in this way, we may produce something new knowledge, new technology, and this make our life richer, and more convenient, and so on.
And that's really the core of the basic science, isn't it? And what divides it from the applied sciences. So it's really important that we do this research and with open minds, of course. We are running a bit out of time, but I will have a few more questions. We don't have time for all the questions here, but there's a really simple one that may have a long answer that I was intrigued by, and that is what makes a nucleus stable?
Proper combinations of neutrons and protons. So
okay, that was an easy answer.
Elements should be more or less equal number of protons and neutrons. For example, carbon 12, most stable isotope of carbon is 6 protons and 6 neutrons. Oxygen 18, 8 and 8, and 16, sorry. For heavier elements, proportion is a little bit different. For example, for uranium, number of neutrons should be 50% more than number of protons, and that is most stable combination.
What counts as stable? Is that more than 1 second, or is it stable for eternity, or is
for uranium? No, for uranium, billions of years. So yes. Most stable isotope of uranium, uranium-238, lives 4.5 billion of years. That is half-life.
What about elements 118 and so on?
118, the only isotope we know lives a little bit less than millisecond.
Okay. But is it then a goal to make it more stable for a longer period of time, or is that not of interest?
Of course, it would be interesting to find even more stable super heavies, but for that we should come closer and closer to the island of stability. For that, it is not clear how to go. All our methods gives insufficient number of neutrons. The number of protons, element itself, I don't say that it's not a problem, but it is solved problem. But number of neutrons in a nucleus, it is a problem. We always have insufficient number. So we succeeded to touch the island of stability, but not to reach its center. And when we touch the longest half-lives which we saw, they were about a minute.
Okay.
A minute. But predictions for the top of the island is maybe thousands of years. Thousands of years.
Okay. I will continue on that note by giving you the last question here, which of course would be, I'm passing it on. Would you dare to guess when we will see 119 and 120 detected?
I also want to know the answer on this question.
And will it be in
step by step, we already commissioned this facility. We made all these test experiments. Last year, in November of last year, we made the first experiment on synthesis of element 115, already known, moscovium. And now, these days, we have experiment on synthesis of element 114, flerovium, which is also known. But already now we see that this equipment is much more efficient, tens of times more efficient than previous equipment of previous generation. And step by step, we go to this goal to synthesis of new elements. Maybe next year.
Next year, okay.
Maybe next year. I mean, next year we will start this experiment. Making something new, you never know how successful, how lucky you will be.
And maybe next year you can even travel again and come to Oslo. A lot of miracles can happen. So, yes. Well, thank you very much, Dr. Alexander Karpov. This was a really interesting lecture, and it really gave us some food for thought, all of us listening here. So thank you very much for your lecture, and good luck with the hunt for the next elements.
Thank you very much. Bye.
Goodbye. Og takk herfra også.